We have with us today Susan MacKay, who's a co-founder and CEO of Helix. Susan earned a PhD in chemistry from the University of North Carolina, Chapel Hill, and a BS in chemistry at the College of William and Mary in Virginia. She has started and run 2 different companies in Maine. Prior to this, she worked in corporate research and development at 3M in Minnesota and did product development work at Physical Electronics. And that's all I can do for a bio for Susan, because all you industry folks are you don't talk a lot about yourselves. So I'm going to let her just dive right in and let us know about her work. Thank you.
So thank you again for having me. So I'm here to talk to you today about my company Helix and the technology we've been developing and what's unique about it in terms of the science that underlies it. So our motivation at Helix is to address a growing concern of the inaccessibility of fresh water and how can products like ours enable more efficient use of freshwater resources. So as you've heard already today, the world is mostly made up of water. However, what most people don't know is that only 3% of the water on Earth is fresh water, and out of that, less than 1% is accessible to humans. And so in Maine, we have abundant water. However, you don't have to go far in the U.S. and across the continent to find regions that are under extreme water stress. And in fact, by 2020, nearly 2/3 of the world's population is going to be living in a water-stressed region. Water stress means you don't have good access to clean, fresh drinking water. So globally, the majority of water, the fresh water, is used by agriculture. But in developed countries, there's a very different story. As countries develop and become more industrialized, more than 50% of their freshwater resources is diverted to industrial use. And in fact, in countries like Denmark, it's more than 90% of their fresh water is consumed by industry. So what we have developed at Helix to address this problem is a technology that's widely used to clean water, which is known as filtration. Now, a filtration unit shown here is mostly filters surrounded by pumps and other and tubes and control units. And each of these filter units is encompassed within this. So a single filter, you can have many of these filters. And the more filters you have, the more water you treat. So at Helix, what we've done is we've developed a coating that we apply to the inner surface of the filter. And what's unique about our technology is we've actually used DNA. We've mixed it in with the coating material, which is a ceramic. We then remove the DNA, leaving behind very small pores that are actually less than a nanometer in diameter. And in fact, these pores are what does the separation. So when water flows through these pores, they're so small, they can actually remove dissolved components in water. So with our filter, we can filter sugar, salts, even dissolved oil out of water. And what people really like about our filter is that they're made out of ceramic. So here's some examples of the filters that we can actually coat with our technology. These are the type of filter geometries we're coating now in our lab up in Orono. The more channels you have, the more surface area the more water you can treat per tube. So like I said before, you can have a small system, like shown here, to treat smaller volumes of water, up to very large systems to treat up to what they call 100,000 barrels of water a day. That's the largest system that we're currently conceptually working on. So one of our current customers is interested in using our technology to eventually treat that volume of water per day. Now, in the U.S., most filters have always traditionally been made out of plastic or polymers, and they're very cheap, and they're used ubiquitously for treating drinking water. However, for industrial water, they have a problem in that they tend to foul due to boiling water. They can also dissolve, so they don't withstand high temperature or solvents or low pH very well. So we use our filters for industries where they can't use the current type of filter technology. One of our customers is in the emerging biofuel industry, where they're trying to convert agricultural waste to fuels and chemicals. Right now, if they're going to try to do that conversion, they can't use filtration because the polymer filters don't work. So they have to use very energy-intensive processes, things like evaporation or where they're boiling off the water to concentrate the sugar. So they use our filters to concentrate the sugar. We also work a lot with the oil and gas industry here in the U.S., where they produce a lot of contaminated water when they extract water from deep in the earth using things like fracking or steam-assisted gravity extraction in the oil sands of Canada. And they're interested in recycling a lot of that water. So right now, the oil companies that talk to us, either because of regulation or because they operate in a part of the world where water is scarce, they would like to take those 100,000 barrels of water a day that they're producing and actually repurpose that water to agriculture. And in fact, not just regulation, but also, as we all know, when they try and re-inject or dispose of that water, a lot of times what will happen is we've all read in the paper they can create earthquakes or even contaminate the surrounding groundwater. So for instance, this is a project we're working on now where this is the process where from the left they separate all the oil and water out, and they actually have to go through a complicated series of steps on site, which they were surprised. They went out to the water treatment industry and found they had all these steps to get to the water they needed. With our filter, they can do the same thing with a savings of 94% of the energy. So this is a picture of some of my team and some of the people who supported our research today. So with that, I'd like to thank you for your attention.
What I should have put in with Susan's bio is all the TED Talks and the different pitches that she does. Like, she's an old hand at this.
Talking fast.
Talking fast. Any questions that we can start off with?
Technology.
Yep, yeah.
You're actually creating a size barrier for the molecules you don't want.
Yes, it works in two ways. The holes or the pores in the filter are so small, it both works by size exclusion, and there also can be some, it's called molecular separations. So that there can be a charge on the surface of the filter that actually repels some of the molecules. So there's two different ways it can interact.
So the molecules you don't want don't foul that filter, they go on somewhere else?
Yes, so the way our filter works in process is a process called cross-flow filtration. So the majority of the water goes straight down the tube, and then we coat that inner surface and we apply pressure. So we don't get much, and our pores are so small, we don't get irreversible fouling. So things don't clog up the pores. We get surface fouling on the surface, and then we do a clean in place step to clean it off.
What kind of DNA?
We can use any DNA.
Seriously?
Yeah, the reason that's usually the first question I get asked, is why DNA? DNA is actually very unique. It's got a business case and actually a chemistry case why we use it. It's the size and shape and the chemistry of DNA allow us to make an exact length that's identical. So we take a certain length of the DNA, and then the chemistry is such that it interacts more with the ceramic material. So we've actually, all our IP is and all our trade secrets are how we get the DNA to dissolve in the ceramic so that it interacts and spreads out and disperses before we apply the coating. And so that way we have individual strands of DNA that are dispersed. And then because it interacts with the ceramic, the pores are small. You can use other types of molecules, but the pores are actually larger. They're almost always like 2 nanometers. But with the DNA, we get what they call 6 angstroms, so less than a nanometer size pore. And then it's a business case because it's readily available.
Right. Go ahead.
How much does this cost compared to the conventional?
Compared to other ceramics, it's nearly identical because the DNA costs, let's say we sold the tube for $100, the DNA cost is less than a penny. So we're not adding a lot of cost by using DNA. So ceramics are more expensive than plastic filters, but they last longer and they work where the polymers don't.
Is the waste that you filter usable for anything?
I mean, we don't always filter waste. So sometimes it's not. Sometimes our filters are used to separate. So they separate a value-added product from a product you don't want. So it all depends on how the filter's used. But in the oily water case, no, you wouldn't reuse that waste. But what you've done is you've concentrated it down, so now you can dispose of it more effectively. Instead of disposing of large volumes of contaminated water, you've pre-concentrated the more hazardous material to a smaller package.
Tamara?
Do you use this for drinking water, or
Um,
not so much?
It's beyond the purity needed for drinking water. With drinking water, you want to get rid of viruses and bacteria. We could be used for what I call first world drinking water problems. If you want to get rid of like pharmaceutical residue, drug residue from water, things that might over time cause cancer. But for basic drinking water, you really just want to get rid of bacteria and viruses, which are much larger.
Well, can I try to put it into context? Would this be like reverse osmosis, or would it be?
We can be used in conjunction with RO, but we're not quite high enough purity to remove all the salt from water. So we'd be a much more expensive option in that application than what you're doing with the polymer filters. So.
How long does it change the filter, like at a certain amount of water?
That's a very good question. That's called permeance. So that's how fast our filter can work. the more pressure you apply, the faster you can filter. And so there's an energy and time, there's a cost trade-off for how fast you want to filter, and because the energy costs more, at some point it's going to not be a payback. But in general, we haven't actually, we're less expensive than an RO filter by like 30% in terms of treating water, is usually how we explain it to engineers.
So RO is reverse osmosis, which is
Yes.
this really funky thing that you can ask Susan about after. It's really cool. Go ahead.
You have to have like 5 million people spit in the cup.
Well, we thought as a fundraiser we could get wealthy people to donate their DNA, like have an auction.
That would be really cool.
No, we actually buy the DNA. It's a byproduct of the biotech industry. They use what we call the cheap DNA or natural DNA. Like, for instance, in Maine, we can get it from a company that extracts it from the fish blood as a byproduct of the aquaculture industry. We've also used what we call synthetic DNA, where you can actually make your own DNA, like DNA oligos. And we've done it both ways to try and determine ourselves which one's more cost effective.
That was fantastic.